All right. So we're going to kick this off and just do a brief announcement of who I am, just a quick little introduction. My name is David Berkowitz. I'm with Montrose Environmental. I have a background in, so I've been with Montrose since about 2015 as part of an acquisition with in my legacy company, Enthalpy Analytical. My career has been kind of based in measurements, both source sampling and ambient monitoring. Done a lot of work with passive sampling in the refining sector and TO15 and of course source real-time measurements, field measurements. Ethylene oxide is one of those things that kind of cropped up as a premier issue maybe about 3 years ago or so, so started working in that space with a focus on that and identifying new ways to measure, given EPA's IRIS assessment with the 100 to 100 million cancer risk, inhalation risk at roughly 20 ppt. TCEQ did a similar toxicological study, and their 100 to a million is roughly in order of two orders of magnitude higher than EPA. However, in recent events, EPA's MON ruled they're moving forward with the IRIS risk number, and that's a bit controversial. But anyway, which the whole reason for my talk, really. So, we've got this really low risk, inhalation risk concentration, and technologies and approaches to measure concentrations down in that level really were not existent, or at least not validated, ruggedized, if you will. So part of that's what this talk is going to be about. Just going to cover various technologies and approaches. I'm going to break it into 3 parts: source testing and monitoring. So we'll cover pretty much historic approaches like gas chromatography, FTIR, optically enhanced FTIR, and we'll talk a little bit about continuous emission rate monitors, as those we anticipate a need. Well, there is a need for those, and we anticipate a greater need moving forward. Part 2, we're going to discuss ambient measurements. We're going to look at PTR, time of flight mass spectrometry, mobile lab, and kind of how that works. TO15, and not here on this list, is cavity ring down spectroscopy, something that we've kind of looked at as well. We're using that technology currently for methane, but they have an analyzer that'll do ethylene and oxide as well. So I'll cover that. I got one quick slide on that, and then part 3, which is really just one little slide, I'm going to talk about some method development, potential future method developments for laboratory methods of analysis. So with that, let's kind of get into it here. GC, been around for ages. Basically, you've got an analytical column. You got some way to inject your gas sample from a source testing standpoint. It's usually a 2-position valve. You've got a carrier gas that sends the sample through the column, separated by its individual components and detected with a detector. Been around for years. It's well established. It's in EPA rules. It's part of permits, part of Subpart O and all the niche apps. And so, disadvantage of this approach, it's not really continuous. It's semi-continuous. You take your data points and you've got to wait, 10, 15 minutes for the separations and then the detection to occur before you can take another snapshot. Over to the right, you can kind of see this is a real-time measurement over time of a process of ethylene oxide from commercial sterilizer to a wet scrubber. You can see that your emissions with your first evacuation, you got a room, sterilization chamber full of ethylene oxide, and you pull that out, send it to your scrubber. Your concentration is high, your removal is good, but still removal from a percentage standpoint is still a larger number, right? So as that evacuation occurs, you can kind of see you evacuate, refill, your concentration goes down. So each time you take a snapshot, you could catch a high or a low, and then you have a run average of these data points randomly selected. Is that really representative of your average concentration? So that's a disadvantage. Another disadvantage is, your FID is typically your detector on here. It's not selective, so your chromatography has to account for any kind of interferences, and acetaldehyde is definitely one of those candidates that can kind of bugger things up. Which we'll move on to the next slide. These are some chromatograms. On the top is ethylene oxide peak. The second one is ethylene oxide and acetaldehyde. Now, this particular method was developed to actually resolve these, but in a lot of instances, there are gas chromatographs that are not configured to separate these two things, and you can kind of see that these are pretty close together with an optimized approach. On the bottom is a stack sample, and you can see this small peak out there. If you have retention times moving around, which can happen with moisture and things like that over time, it can get kind of confusing, or you can have a coalition, and so you're biasing those results. So this is something to watch out for, and definitely a disadvantage. So to kind of move on from that, we go to FTIR, which stands for Fourier Transform Infrared. This approach is basically you have IR radiation, which is passed through an air sample in a gas cell, heated gas cell. Some of that infrared light is absorbed, and then you have transmittance through to the detector, what isn't absorbed. And the resulting spectrum just represents, it's an absorbance spectrum. And from that, you can pick out the different bands of infrared light that are absorbed. That gives you a spectrum, and you can match that up and quantitate off of those different wavelengths of absorbance wave numbers. And this is an example of an interferogram infrared spectrum. You can see you've got your transmittance and then your fingerprints. With this particular approach, the advantage is it's continuous, and that's what you saw on the GC first GC slide or the second GC slide with the line that kind of gave you concentrations over time. The disadvantages of this approach is that every source is different. From a commercial sterilization or medical products manufacturing source, it's pretty simple. But then you take this out to a chemical facility, and each source is going to be different, and so it will take quite a bit of skilled spectroscopist data analysis to really deconvolute the data, remove interferences, and write a recipe to actually quantitate in that source. So that's a disadvantage. So if you're getting that done, you definitely want to make sure you have a qualified team experience with that. Typical detection limit for a standard FTIR is about 200 ppb. And again, this is going to depend on the sample matrix. Moving on, this is optically enhanced FTIR. So you take a standard FTIR and then you put a filter in there. And what that does is that eliminates the bands, the wavelength of light that actually gets through. And in doing that, you can turn up the intensity of your IR and lower your detection limits. Now, you don't eliminate your interferences, but you do kind of set it up in a way that you're going to limit your interferences. This is also a continuous approach. Detection limit is way better than just the standard FTIR down at a half a ppb, roughly. And again, this is matrix specific. And then the selectivity is made better through the use of what's known as a TOM, or thermal oxidizer module. And what that does is it takes a sample of your sample gas and it runs it through an oxidizer module that's heated to about 125 degrees, and that oxidizes all your ethylene oxide. But then it'll leave your typical interference candidates in there as a background that gets subtracted from your spectrum. So you can really efficiently subtract out your interferences to give you a better number. Disadvantage of this particular approach, it takes really specialized training. Again, like FTIR itself, our organization has a lot of spectroscopists, and we have fewer spectroscopists that are operating this particular equipment. So we can take this particular piece of equipment, which is packaged as a continuous emission rate monitor. There are state regulations. Some states are requiring this. The state of Illinois was the first one to require this. And so, we did an installation up there. The state of Georgia is doing it. There are a number of states that are talking about implementing this. We also anticipate this is going to be part of federal rule for the commercial sterilizers, which I think is, they say, going to come out beginning of Q4 this year. These particular instruments are qualified using performance specification 15 and 18, which kind of are not specific to ethylene oxide, but they're good working documents to qualify these instruments. Moving forward, technology neutral performance specification 19, we expect that to hit the books, and that'll allow the use of something besides FTIR. It's technology neutral. Right now, 15 and 18 are specific to FTIR. So, as I said, these are field-proven solution for real-time analysis, ongoing permanent installations of a continuous emission rate monitor for ethylene oxide. It's continuous. They're available as a single port instrument, but it also has a 4-port multiplexer, so you're able to analyze up to 4 emission points at one time. An advantage of this, even if you have a single compliance point, you could conceivably, you may have a serial emission control devices, and you can kind of take samples at various points along the way to kind of evaluate your removal and maybe catch a problem before it actually becomes a real problem through looking at these different points along your process. Detection limit is, as I said, about 1/2 ppb. But again, dependent on source composition, and it does use the thermal oxidizer module, just like the stack testing approach. With that, we're going to kick it over to ambient air and fence line sampling studies and things. So for ambient air, we can use ambient air and indoor air. We can use optically enhanced FTIR with multiplexer. That's got 20 ports, up to 20 locations you can monitor. We use mobile PTR time of flight mass spec as well. As I mentioned at the outset, mobile cavity ring down spectroscopy, and then standard, kind of TO15 sample collection and analysis. And we'll kind of go over each one of these things, their advantages and disadvantages. So FTIR spectroscopy, with these particular instruments, they're kind of like continuous emission rate monitors, but we call them continuous monitoring systems, CMS. So with these, we've actually deployed these as area monitors for chemical sterilizers, medical device manufacturers. And this particular picture over to the right is 2 of the units deployed at one. So we've got 40 different locations with tubing runs up to, I think, nearly 1,000 feet. So you spread these out, giant pump through there. So there's a single pump which actually primes all the lines continuously, and then you've got a selection pump which actually will sequence through and then take each one. You get a measurement about every 30 seconds. This is available in both a standard configuration, standard FTIR configuration, which is about, again, 200 part per billion. And then with the optically enhanced star boost trademark, down about 0.5 part per billion. So also with ambient PTR time of flight, a mass spectrometry can be used. With this, basically, it's a chemical ionization process, a soft ionization. You've got a hollow cathode with, in a standard configuration, a hollow cathode with kind of a water inlet vacuum, which actually pulls your water up in there and you get a soft ionization where you add a hydronium ion to your primary, compound. So in the case of ethylene oxide, it would be 44 is the mass. So what would come through down the time of flight drift tube to the top MS, you would read a mass of 45 for that particular compound. You can, with this approach, you can read virtually any organic compound, and you can do a number of compounds at once. I know we were doing an odor study, I think evaluating 250 compounds at a clip. This is, highly temporal, talking about a data point every second down in the PPTs. It's, as I mentioned with hydronium approach, you got acid aldehyde problem, right? Because it has a mass of 44. So both of those, you're not going to separate those with the time of flight. So as I mentioned, it's chemical ionization. We use a oxygenyl approach, and that ionizes acid aldehyde differently than ethylene oxide, and you're able to get separation, mass separation through that. This is just a screenshot of what you're monitoring. The graph on the top is all your masses. So you hit all your masses at once, so you can kind of see what's popping up from the mass standpoint. On the bottom screen, this particular view shows two compounds that you're monitoring the ongoing concentration to. One's in the red and one's in the blue. So you can set up your peak table and monitor those concentrations, and you'll kind of see them wiggle or waggle as the concentrations go up and down. This is the command center. So as you see, we got it set up with gases. We can install various analyzers in here and do a number of other things at a time, but it's very well thought out. We use it for mobile applications for the most part. So usually we'll kind of get into a plume, and then we'll move it and then stop and take readings there. This is a pretty cool tool. We actually have it parked out front. I'm not sure how long it's going to be here today, but it's parked out in front of the hotel. So if you get a chance, maybe pop down there and check it out. There's 3 of them built out like this in the US. They're about $1 million to build for each of them. Pretty universal, can use them for a lot of different things. Those are just some examples. As I said, you can measure virtually any VOC with that. For ethylene oxide and oxygenyl mode, we can measure down to around 70 part per trillion with a measurement about every second. You can do time averaging to lower that a bit. As I said, it's mobile, and you combine it with meteorological data, can use it to kind of trace down plumes and sources. A disadvantage of this, so there's a little bit, it's a little pricey to deploy, but really there's no EPA method, so you can't really use it from a compliance standpoint. But we are in talks with EPA, working out a method or an approach to kind of put in place as maybe a conditional test method or something like that. EPA is pretty busy right now. That's kind of stalled, but it's something that we've had talks with them about. This is a histogram of, an ethylene oxide runs around an airport and through a community. And you can kind of see all the data points in the various concentrations. You see how you can get into a plume and really kind of use, you can visualize how to use the meteorological data to kind of help you trace concentrations and tell you more about what's where and where it might be coming from. Along, again, in the mobile, from a mobile standpoint, we have a cavity ring down spectroscopy mobile laboratory. This was actually built originally for mobile methane monitoring. But the cavity ring down spectrometer actually will do ethylene oxide with a different configuration. So we've kind of demoed this. We've given it a shot. That particular device will measure ethylene oxide, methane, carbon dioxide, and water vapor all at one time down in low PPT levels. It's continuous and mobile, and with the meteorological data, it can do the same things as the PTR. So that's one of the reasons why we're investigating using it. But definitely the methane is a pretty cool tool. Again, there's no EPA method for this. Usually this is used for, kind of investigatory work, and therefore you don't need that. So move on to TO15. Probably everybody in this room has heard of TO15. It's been around since the dark ages for measuring. It's a great approach for measuring organic volatile compounds. Use canisters and flow controllers. When ethylene oxide became a problem, nobody was measuring ethylene oxide via TO15 regularly, and certainly not down in the PPT levels. So there was a bit of work to do to kind of ruggedize TO15 for this. Our laboratory, Enthalpy Analytical, started working on this years and years ago once it started being brought to our attention by EPA. And the things that had to be worked on with this are kind of familiar topics from the other things that we've talked about: selectivity, precision, detection limit, stability. Those are main focuses. Basically, I covered this slide. It's a common analytical testing method with lower detection limits. Not low enough originally, operated in a full scan mode, but you can do a selective ion monitoring approach. And with that, you can get down to roughly 20 to 40 PPT. People like the approach because it's unattended. You can deploy it, let it go for 24 hours, up to 72. Disadvantages, again, interferences, stability in the canister over time, and it, because of all these things, does require an experienced laboratory. These are the tools used to collect samples. You got your specially evacuated canister. It has to be Siltec or Silanite, basically a coated inert surface. If you don't have that, you'll end up with breakdown products, and ethylene oxide will turn into other compounds. And then we've actually seen issues, or we've heard of issues. I have not actually seen it, where you have what's known as growth in the canisters. And this is from not having the canisters cleaned properly. Your laboratory's got to heat and purge these cans in a certain way to prevent that from happening. And then you got to have the coated canisters. Ideally, your flow controller, your sample train is going to be Siltec or Silanite coated as well. Analysis is typically, our laboratory uses an Agilent GCMS, operated in SIM mode, most typically for detection limits down in the 20 PPT range. They use an NTEC sample pre-concentrator 7200. What that does is it will take an air sample, run it through a cryogenically cooled, liquid nitrogen cooled cold trap, and then heat that and desorb it and do the gas chromatography like we kind of saw on the front end with a high resolution column. Potential interferences with this are going to be acid aldehyde. Again, mass 44, mass 44. That's a problem. Methanol, from a mass spectrometry standpoint, shares some of those. You have small molecules, you're going to have similar ions from an electron impact. Trans-2-butene is something that APA identified as a potential interferent, and then just in general hydrocarbons, given the low AMUs. Our laboratory method development started the GC oven temperature down at about 10 degrees. You can kind of see there in the middle of that circle is your ethylene oxide peak. You can see cis and trans 2-butene over to the left. And then you got your C5s out there to the right. This is another trace here, starting the oven at 10. These are your organic compounds. You can kind of see a tiny little blip down there to the left, which is acid aldehyde. Then you've got methanol, which is on, right next to your ethylene oxide peak, which is a shoulder on bromoethane, which can be spectrally resolved easily. It doesn't have any overlapping fragments, ion fragments. So here's your typical ion or mass spectrum of ethylene oxide with primary masses of 15, 29, and 44. We'll flip here and kind of compare acid aldehyde and ethylene oxide. While they're not the same, they have a good deal of similarities, especially with those primary masses. So there's where resolution is really important. And then we'll just move on to methanol. You can see that there are some of those same mass fragments there. And then trans-2-butene, I just wanted to show this here. It does share some of those, but then you've got your mass 56 there for your butenes. If that shows up in that window, then you have a problem. So that's more of kind of a qual ion. So your chemist would look at it and say, okay, I got mass 56. I have a potential issue here, and then look to try to resolve that. So as part of the method development, there were 2 stability studies that were run. Took some canisters and humidified them and spiked them with 40 part per trillion of ethylene oxide and held them for 34 days. You can kind of see these 3 canisters, the concentrations kind of bounced around, but that's really due to instrumentation sensitivity changes over time. They kind of track with each other, if you notice. And then your trend line, you stay pretty close to 100%. So pretty good stability over 30 days in these silanite cans. Interestingly enough, we did some that were unhumidified. You can definitely see you got quite a bit more degradation going on there. So your moisture is actually preventing interaction between your canister and your compound. So something important to note. This is also 40 ppt. Stability study 2, the laboratory took 2 field samples, just kind of picked at random, and did analysis at day 27 of those canisters, and then continued on through day 64. And you can see for the first sample, you got a difference of like 22% actually on the high side. And then on sample 2, 1.5%, a little bit on the low side. So very stable over time. But we're getting mixed, we're hearing mixed things from EPA and others who are doing research. And then as far as method development is concerned, there are some things in the works. Right now, there's sorbent tube methods that are written. There's a NIOSH method using hydrobromic acid coated tubes, which actually derivatizes your ethylene oxide, allows you to concentrate it that way before it gets prepared for analysis. This is available both in a pumped and a passive. The passive approach, both of these actually have a limited volume or limited amount of time you can use them because they're sensitive to moisture. And as you know, ambient air and stack, there's moisture in there. So you're going to use your reagent up. So there are some things that can be done to optimize these further. So I'm not saying that they're being done, but there are some things that can be done. And moving forward, to address these compounds of interest, we're going to have to try to do method development to address measurements at these levels. Passive tubes as well. I know EPA would love to have a passive tube similar to what's being used on the fence line of refineries for benzene. It's not a great candidate. You got a really high vapor pressure. So something passive, it's just going to come back off. I think probably there's still some more research that can be done. Maybe there's some things that we've done with some sort of a reagent to trap it. From a stationary source standpoint, typically measurements are done with GC. Kind of roll back to my first slide, either with a direct interface approach or a Tedlar bag approach, with a detection limit down around a half a part per million. Half a part per million really ain't going to cut it. So, we were involved with some method development. I was a lot of years ago using an impinger solution that was alcohol-based and had an inorganic acid in there, HCl. And you bubble through that to concentrate your sample, and then you form epichlorohydrin as your derivative and analyze that using an ELCD to get your lower detection limit. That's been somewhat validated, but there are some issues with that. It still needs further work, but these are just ideas of things that can be done and investigated to lower detection limits. And with that, I'm just going to open up the floor to any questions.